Hello, I'm Vlado from ViDiLabs. In this video, I will show you a couple of case studies on how you can use the ViDiLabs calculator with thermal cameras. I covered the thermal camera technology in a free video called Special Cameras, which you can find on the ViDiLabs website at vidilabs.com under the ViDiLabs Academy tab. But for the purpose of this case study, let me summarize that thermal cameras we use in CCTV are in many ways similar to the visible light cameras. The main difference is that the thermal sensors are made with a slightly different technology to the visible light CMOS sensors. One of the most popular thermal sensor technology is known as microbolometer technology. Thermal sensors have much larger pixels than what we use in the visible spectrum. If a typical CCTV CMOS sensor has around 2 micrometers pixel size, in order to pick up visible light from 400 nanometers to 700 nanometers, the microbolometer pixels are typically 17 micrometers, and they are designed to pick up thermal wavelengths from 8 micrometers to 14 micrometers. These wavelengths belong to the long wavelength infrared range, or LWIR, and they contain the heat radiation various bodies produce. The hotter the body, for example a living human being, will produce higher energies which the thermal sensor picks up as brighter light. Basically, the thermal sensors see like black and white sensor, which the camera software then maps each different intensity to artificial colors in order to indicate which part is hotter. If there is a reference heat source in the field of view, with a known temperature of radiation, it is possible to calibrate such temperature so that object that you see can give you a relatively accurate representation of such object temperature. Of course, like with visible spectrum cameras, the size of the pixels, quality of the optics, and the processing electronics will define the precision of such measured temperatures. One should consider also the atmospheric conditions between the object and the thermal camera, such as smog, fog, dust, rain, or snow. Because thermal sensors have large pixels, they typically offer much lower pixel count than high-definition sensor, for example. Also, because of the specific technology, which is not produced in mass market production like the visible CMOS sensors, they tend to be more expensive. So typical low-cost thermal sensor these days would have something like 160 by 120 pixels. The more expensive and more accurate sensors would typically produce 320 by 240 pixels, or even better, more expensive sensors would have 640 by 480 pixels. Now, it is important to know that the thermal sensors use lenses like the visible cameras. Just in this case, the glass material for those lenses is chosen to be transmittive to the LWIR range of wavelengths. Typical material for this is germanium, silicon, zinc sulfide, or chalcogenide. Apart from these differences from the visible optics, the rules of refraction and focusing are the same. This means we can use the ViDiLabs calculator to make similar calculations for the angles of view, distances, and pixel density. Here, however, when using pixel density, we have another major difference. While in the IP CCTV we use the 62676-4 IEC standard for pixel densities, and the subsequent corrigendum we from Standard Australia submitted, about which I have made a number of videos, so if you're interested, please check them on our website. The thermal industry uses pixel density references which were very different to this. My colleagues from Infinity Optics in Canada were very kind and provided me with a very nice white paper which explains how this thermal DRI standard became. So I would like to read to you so that we can make the same case studies calculations based on those DRI standards. So here it is, what you can see as well. So what is DRI? DRI basically stands acronym for detection, recognition and identification, but it is different to the so-called DORI, which is also referring to detection, observation, recognition and identification, because it's seen from the thermal imaging perspective. So let me read this to you, because this might be very interesting to know if you haven't already been acquainted with this terminology. DRI is a universally accepted set of standards that attempts to provide a means of measuring the distance at which a thermal sensor can produce an image of a specific target. These standards were initially developed by the US Army in the 1950s and unfortunately have not been updated much to account for newer technology with larger theoretical ranges that are less likely to be achieved in the real world. The model is based on a 50% probability of achieving the following objectives under ideal conditions. Please read each definition, as they may not match what you would expect from reading the terms alone. So, thermal detection. I add the word thermal in order to differentiate from visual detection. So, thermal detection refers to the distance at which a target initially appears in the image. This target is something out of the ordinary that is warmer or cooler than the ambient environment. Specifically, it will be visible on at least 2 pixels, so there will be not enough information to confirm what the target is at this distance, just that something is there. So that's thermal detection. Thermal recognition. Contrary to what might be expected, recognition does not mean that you can recognize an individual. So this is the difference between visual recognition. Recognition refers here to the distance at which you can determine an object class. Is it a human, animal or vehicle? And then we have thermal identification. So thermal identification refers to the distance at which you can differentiate between objects within a class. For example, identifying the type of vehicles, truck, SUV or car, or whether the human is a soldier or civilian. So these are the so-called DRI, thermal DRI pixel densities, and I will show this on the table as well, so that we can use them as a starting point for when we do ViDiLabs calculations. Okay, so let me just open this table that I have produced for you. So this is basically showing detection, recognition and identification for the thermal vehicle, thermal human, but also for the IC definition of that, and for the ViDiLabs or Australian standard corrigendum that I spoke about in the past videos. So as you can appreciate, for the thermal vehicle pixels per meter, in order to detect it, it's enough to have at least 1 pixel, possibly 2. Now clearly here you will really very much depend on the clarity that produced by the thermal optics. If the optics is not sharp enough or it's not focused, it will not give you 1 pixel clarity. So it's important to know that this is really on the edge of what the actual optics can detect. So for thermal vehicle detection, you need 1 pixel at least. For the recognition, you need 2 or 3 pixels per meter. And for identification, you need 5 to 6 pixels per meter. Now for thermal human detection, you need 1 to 3, so anything between 1 and 3 at least. You may differentiate between a vehicle, like you can see upright, maybe 2 pixels, 3 pixels going in the vertical direction rather than in the horizontal. Then to recognize if it is human, you need 3 to 7, and if you want to identify whether that's really a person, it's not a dog, it's not a car, you need 6 to 14. So we will use this in order to do some of our calculations. Okay, so let me now open up a specification of a known thermal camera manufacturer. Don't need to disclose any brand names because there are a lot of them that are very similar, but just to give you an idea how I would calculate certain things. So let me share the screen. So as you can see here, these specifications show 2 modules of the dual sensor camera, the thermal module and the optical module. So this is a camera that in one box you actually have the visible and the thermal camera. So for the thermal camera, this is the important thing we need to calculate, because I've shown what we do with the visible part in any camera with a ViDiLabs calculator. Let's take the thermal module as an example. What you will notice is, unlike with the visible spectrum like optical module here, it tells you what is the image sensor. And if you remember, in the ViDiLabs calculator, the first thing we needed to do is know what is the actual physical sensor size and the resolution in order to calculate all the parameters, angles of view, pixel density, distances, and so forth. Now, typically in the thermal module, you don't have that because they're using larger pixels and probably they are not very standard visible imaging sensor sizes. But most of them will give you pixel interval, they call it, or pixel pitch, or basically in a way this is pixel size per individual pixels. So as you can see here, in this part, we are showing 17 micrometers pixel size or pixel interval, and this particular thermal module has 160 by 120 pixels. So this is really a very small microbolometer, which actually is subclass of that called vanadium oxide uncooled focal plane array. It's of the same technology that I mentioned in the introduction. So what we need to do is we need to multiply 160 by 17 micrometers and 120 by 17 micrometers, and then we'll get the actual horizontal by vertical pixel count in order to enter it into the ViDiLabs calculator in order to calculate pixel density to see how far we can see human or vehicle and what that will bring as a result. Now, one little clarification here. It says the resolution of output image is 320 by 240. A lot of thermal cameras will do that, so that means they do internal upsampling from the 160 by 120 to make a bigger picture, because 160 by 120 is very little, so they upsample it, which we are not going to use for calculation because that's actually artificial, so it's not genuine native resolution of the sensor. This is achieved in order to make the picture bigger, so often the dual sensor cameras may even have overlaying of the thermal imaging over the visible spectrum. So as you can see here at the bottom of this optical module, we've got a resolution that is much higher than, let's say, HD, 2688 horizontal by 1520 pixels. So basically, to overlay this, they first upsample it and then they again amplify it or stretch it in order to fulfill the same view, so you can see if a person goes in there what it looks like. In fact, maybe I should show that now. So let me open this image. This is something I've been experimenting in with dual sensor cameras. So let me switch and share this image. All right, so this is an image I have taken of a dual sensor camera. The top one here being thermal. As you can see, black and white image, where the hotter one is brighter. Now clearly you can artificially recolor it. You can make it red for hot and green for cold. That's only artificial after the camera seeing the image. In this case, I am holding a match that was lit, and you can see that the thermal detects here more than 158 degrees in that area. It's actually more than that, but this particular thermal camera detects up to, I think, 150, 160 Celsius. In any case, you can see this is showing you a hot area relative to my body, and this is the visible spectrum camera on the same body that actually sees it. So this can be superimposed on the same visual spectrum, but that information of what is the maximum temperature achieved of 158 is overlaid on this video. So this can be used for systems where you don't want to see the thermal, but it's overlaid as information where that is showing you high temperature. Now clearly we did have here some kind of algorithm to detect fire as well, but this is just showing you how one body camera with dual sensors will look like, showing you thermal and visible spectrum. Okay, so how we go about that? As I said, in order to find the sensor size in millimeters, we multiply 160 by 17, and I have here a calculation that I've already done to make it easier. So 160 by 0.017 millimeters, which is 17 micrometers, is about 2.72 millimeters. So that's our horizontal width, and the vertical, which is 120 by 0.017, will be about 2.04 millimeters. So let me now turn onto the, and just notice here that we've got focal length on this particular example 9.7 millimeters. You obviously would have different thermal sensors with different focal length lenses. You have to know what you're ordering, but in my case what I'm showing here is just for the purpose of calculation. That's just to show you that the ViDiLabs calculator can calculate the angles of view of the thermal camera, which is completely different than what you see here with the visible. So don't worry about them being so different, because as I said, they are being then overlaid artificially by the actual camera if you wanted to, depending on the camera model. So let me switch now to the actual ViDiLabs calculator. So here is the starting point of the default visual page of the ViDiLabs calculator. As we said, the very first thing we need to do is enter in the bottom blue rectangle what is the image sensor dimensions. As we calculated the thermal sensor with 160 by 120 pixels and 17 micrometers pixel pitch or aperture or distance or size, we multiply 160 by 0.017, we get 2.72. so that means the horizontal dimension of the thermal sensor will be 2.72, and the vertical will be, we said, 2.04. So there's the starting point. Now we said that this particular sensor is 160 by 120 pixels, so let's change the pixel count. So instead of having HD, we put in there 160, and vertical we put 120. Okay, so we've got the basic parameters in the blue windows. Let's now change the focal length of the lens. We said in there that it was 9.7 millimeters. Now in order to change the focal length here, which is outlined with red frame, we need to basically unlock it, and to unlock the focal length we need to lock the distance. These are the two that can be locked interchangeably. So if I now hold 1 second on the distance to scene, it will unlock the focal length, which was by default 8.75 millimeters. If I double tap there, I can enter here 9.7. Okay, so there we go. So what we found is that with this particular small thermal imaging sensor of 2.72 by 2.04 millimeters dimensions and pixel count of 160 by 120 of thermal sensor, we have 9.7 mil that will give us then 16 degrees horizontal angle of view and 12 degrees vertical angle of view. Now if we go back to the actual paper, okay, so you will see here, remember 9.7 millimeter we said, the field of view is 15.96. Okay, if you want to be that precise, but obviously that's close to 16 degrees like we calculated and 12 degrees like we calculated. So we now actually prove that the thermal cameras also use optical rules of the lenses they're using. So the focal length of the lens and the sensor size and the pixel count will define not only the angle of view, but obviously we will see later on pixel density as well as distances if we want to find out. So let's go back again to the calculator. Okay, so this is the starting point we had. So let's now go according to thermal detection. Remember we had a table that said to detect a vehicle you need at least 1 pixel per meter. So to have at least 1 pixel per meter, the best way to find out is we need to know at what distance we can do that, and because we've got now the distance to scene locked, we will need to unlock it by locking the focal length, because we know we are using this particular camera, for example. So we hold 1 second for the focal length, and now whatever we change in the pixel density, as you can see, distance will change to correspond to that pixel density for that focal length, for that sensor, for that pixel count I should say. So let's put in the pixel density here 1 to see if we can, at what distance can we detect the vehicle. Okay, so here it says 570 meters. So at least anything closer than 570 meters from this camera, using 9.7 mm lens, we should be able to detect there is something like a little light dot coming up, so we will basically detect it. That's the idea of that. What about the human? That requires 1 to 3 pixels, so obviously it can be anything from 570. I would say probably it's better to put 2 or 3. Let's put 2. So obviously half of it, 285 meters. So if it is 3, we probably come 190 meters. So anything from 190 meters to 500, we probably will pick up a person, detect a person, although not clearly distinguished if it is very far, because it will be only 1 pixel. So what is then to recognize? Now, according to this thermal recognition, we need to recognize the vehicle 2 to 3 pixels, which means vehicle about 200 meters we probably will recognize that's a vehicle rather than a person. If we want to see a person, the thermal recognition is 3 to 7 pixels per meter. So basically we say, okay, let's choose half of it, somewhere in between, let's say 5 pixels. So if we want to be sure, really on about 100 meters we would be confident that this is really a human and it's not a car. And if we want to go further, really to verify that that perhaps is not a kangaroo or a deer, let's go to thermal identification, which requires 6 to 14 pixels. So I would say here, really it's up to you and the precision of the optics and so forth, but I would say in between 6 and 14 would be 14 minus 6 is 8, divided by 2, 4. So let's go to 10 pixels per meter. So if I choose here 10 pixels per meter, at least theoretically, at least 50 to 60 meters, in this case 57, I should be able to quite clearly recognize this is really a human person, a human silhouette, because you will see it as a silhouette, somebody walking. And for a car, the thermal identification, whether it's a truck or normal car or SUV, you need 5 to 6. So obviously we go back down, let's say to 6. So the distance at which with this camera and with this lens we will be able to distinguish of type of vehicle is about 95, let's say 100 meters. So that's roughly an idea of how you can use the thermal calculation distances, knowing this thermal DRI, detection, recognition and identification, and basically be able to create or design a system where with different focal length lenses for the thermal imaging you achieve different distances. Now clearly this is very obvious, but let's just make now an assumption. Let's say we now have the same sensor size, same pixel count, but now instead of having 9.7mm lens, let's say 6mm lens. You can buy 6mm lens. Then clearly 6mm lens will give you wide angle of view, so not 16, but it will give you much wider. And how much wider and how much closer you can get the 6 pixels for that, let's calculate that. So we will then lock the distance in order to release the focal length for the focal length to be changed. So hold 1 second at the distance, and now let's enter here 6mm. Okay, now we lock the 6mm, and as you can see we were before at 6 pixels per meter, so let's put it back to 6. So as you can see here it's 58 meters, so let's say 60 meters. So you need to come closer, or you need to consider with 6mm lens of the same thermal sensor imaging, thermal camera imaging sensor, you cannot see as far as with 9.7, which is quite logical because you've got wide angle of view, which is shown here with 25.5 angle rather than 16 which we had before. Okay, so that's a way how you would calculate. Now let's assume we have the thermal camera which has more pixels, so it's more expensive, but let's say this particular sensor may be with 640 by 480 pixels. So it's not sufficient for us just to change the pixel count, which we can. Let's change to 640 by 480 and vertical 480, let's say. But remember, the pixel size was 17 micrometers. In this case the sensor itself will be bigger because it's got more pixels times 0.017 will be bigger. How much bigger? Let's calculate that. So I'll do a little calculation here. So I have 640 times 0.017, because we said that those manufacturers don't give you the sensor dimensions like we know it in the visible IP CCTV. So 640 times 0.017, horizontal is 10.88 millimeters, so not 2.72, it's much bigger sensor. So if we now double click at the 10.88 horizontal pixel sensor size, the vertical will be 480 times 0.017. That will be 8.16, so this would need to be 8.16 millimeters and 16 millimeters. And now we've got the right sensor size and pixel count for a better thermal camera, which has 640 by 480 in our case. So as you can see here, what is very obvious is we haven't changed the focal length, and suddenly pixel density has gone up in order to reflect the more details that bigger sensor with more pixels will pick up. So clearly now if we go back to the same 6 pixels per meter, we clearly would go to much longer distance. So double tap at 24, enter 6 pixels per meter in order to identify a vehicle, which was 5 to 6 pixels per meter in the table. So we now go back to 60 meters. So as you can appreciate, now we've got wide angle of view. That's an important part. We've got now 84 degrees horizontal angle of view. So you may say, it's the same distance, like before we had about 58.8, but you now have 84 degrees horizontal angle of view, where before you had only like about 25 or something. So that means now with this sensor, with the same focal length of 6, you will have almost 90 degrees. So instead of having maybe 3 individual thermal cameras with a narrower view that can see up to 60 meters, you now can see 90 degrees almost with one camera. And of course, if we now increase the focal length, instead of 6 millimeters, let's now go back to perhaps 9.7 again. So we now hold the distance and change the focal length to 9.7 and lock it. Go back to the pixel density to 6. So as you can see now, we can go up to 95 meters distance to detect a vehicle, to identify a vehicle, whether it's truck, SUV or a normal car. But the angle of view, as you can see here, is narrowed to about 60 degrees, which is still not that bad compared to the previous one, which was very narrow. So as you can appreciate, even with the thermal sensors and cameras, the logic of finding pixel density, angles of view and distances is the same. You just have to be aware that the sensors manufacturers do not necessarily disclose the sensor dimensions as we know them, but if they give you the pixel size and you know the pixel count, you can easily calculate the physical sensor dimensions, and entering all this, you basically be able to calculate anything that you want, and you can design any system to actually fulfill the requirement. You want to cover a particular big perimeter, you want to make sure you pick up the person at about 100 meters, this is the starting point. So there you go. I think this will give you some good ideas of how you can use the ViDiLabs calculator even with thermal imaging cameras. Thank you for your attention. I hope you enjoyed it, and I'll see you in the next video.